This is a CF34 8E flight operation seminar for fan vibration. In 2015, the CF34 8E fleet experienced a number of flight disruptions caused by the fan vibe digital reading on ICAS turning amber. Flight crews confronted by the digital LP vibe indication turning amber described diversions and air turnbacks because the pilots were unsure of the risks to the engine associated with an amber vibe display. Pilots were equally unsure of how to troubleshoot fan vibes in flight. It's time to set the record straight. All machinery with rotating parts operate with some level of vibration. The purpose of this presentation is to provide information relating to N1 vibration as it relates to the digital LP vibe display on ICAS. Our goal is to dispel the misperception among flight crews that an amber vibe reading immediately equates to severe engine damage. Currently, there is good guidance for pilots about what steps they should take when they encounter an amber vibe reading in icing conditions. Through this presentation, we hope to provide pilots operating in non-icing conditions with recommended procedures to reduce fan vibes in flight when the LP vibe display turns amber, before they take steps to divert or shut the engine down. To start this conversation, let's look at the CF34 8E fan blade design. In the upper left corner of the screen, you will see a black and white illustration of the fan blade root. The entire fan blade is cut from a single piece of solid titanium. GE uses a computer-controlled cutting machine to shape the fan contours and blade root assembly. Note that the blade root consists of 4 blade tangs with a hole drilled through all 4 tangs. Now looking at the cutaway, you will see that the blade disc assembly is comprised of 3 separate tangs that are directly attached to the fan shaft. These 3 separate disc tangs fit into the spaces between the blade tangs, and holes in the disc line up with holes in each blade. Each fan blade is attached to the disc by a single retaining pin that slides through the blade disc and blade tang assembly. The fan blades are designed to rock back and forth around the retaining pin by about 2 millimeters in each direction. During early morning pre-flights when the ramp is quiet, you can often hear clicking from the fan blade assembly as the fan gently rotates in the ambient breeze. The clicking you hear is caused by each blade's center of gravity falling by 2 millimeters around the retaining pin as the blade passes over top dead center. To help the fan blade rotate easily around the retaining pin is lubricated periodically by your airline's maintenance team. However, even a properly lubricated retaining pin will experience lubrication degradation over time. The interface between 3 disc tangs and 4 blade tangs creates opportunities for binding. This is where 99% of all blade vibe issues originate. This artist rendering of the fan blade shows the forces acting on each blade while the fan shaft is spinning. The lines at the bottom of the drawing converge at the fan shaft's center of rotation. As the fan shaft spins up during engine start, each blade must be able to move freely around the retaining pin so the fan blade's center of gravity is naturally driven into position by centrifugal force. Fan vibes that vary from flight to flight may be caused by the fan blade center of gravity not being able to rotate around the retaining pin to its natural radial location. The blade illustration shown here assumes the fan blade CG is in its natural position while the fan is rotating. If the retaining pin lubrication has degraded and the fan blade binds, the blade CG may not be where centrifugal force would place it. The result is an imbalance that we see as fan vibes. If fan blade binding is going to occur, it usually happens during acceleration to idle on engine start. Fan vibe readings can be kept in the green fleet-wide if the retaining pin relube is completed often enough that lubrication deterioration does not become an issue. This is a maintenance function. Airlines that carefully track fan vibes through engine trend data have fewer flight disruptions caused by elevated fan vibes in flight. Pilots can help by annotating the maintenance log every time the N1 LP vibe reading turns amber, especially when elevated vibes are transient and QRH procedures are not required. Many flight crews have reported that they became concerned because fan vibes increased throughout the flight. This is normal as the aircraft gains altitude, but it brings up an important point. The green range for N1 fan vibration spans from 0 to 3.9 units. Many pilots ask, is a fan running at a vibe level of 0.5 units safer than a fan running at a vibe level of 3.9 units? The answer is no. However, we are well aware that on ERJ airframes, elevated fan vibe levels can result in higher cabin noise, which may be a concern to passengers. It is important not to confuse passenger comfort considerations with engine performance considerations. To provide a better understanding of why engine operation with digital fan vibe readings anywhere in the green range is acceptable, let's discuss how the engine was designed to accommodate fan vibes. The CF34 8E was certificated to operate at 3.9 units plus a comfortable safety margin for years of flight operations. The fan vibe threshold was determined when the engine was still in development. During that time, when the engine was being tested, we added some weights to the fan and low-pressure turbine and caused the entire fan shaft assembly to wobble as the engine ran. There is a subset of material science called material behavior that tells us if a spinning part is built strong enough to last through 10 million complete rotations, the part will not fail later on down the road. In other words, once we've built a fan shaft strong enough to last through 10 million rotations in an unbalanced condition, we can consider the shaft strong enough to last through years of normal operation. As an added buffer, we put a life limit on the fan shaft, which means the shaft will be replaced when it reaches a certain length of service. Getting back to the vibration test, it takes almost 28 hours of continuous operation at rotational speeds near full thrust for the intentionally unbalanced fan shaft to rotate 10 million times. When the test was complete, the engine was disassembled and inspected for signs of wear. When engine wear due to imbalance was first discovered, we backed off from the level of vibration that caused the wear. This is how we developed the comfortable safety margin I described earlier. It is also where the 4-unit amber threshold on the LP vibe display came from. It might also be interesting to note that the FAA observes and validates the engine test during the engine certification process. What conclusion can we draw from this extensive testing? Continuous operation of the engine between 0 to 3.9 units does not cause damage to the engine. No pilot action is called for when vibe readings are anywhere in the green range. Quite often elevated fan vibes are specific to one N1 setting, given the airspeed and altitude where you are operating. Temporarily adjusting the throttle will move the N1 away from the resonant frequency, causing the elevated vibe level. This is equivalent to slowing down your car when the front end starts to shimmy. Slowly reduce thrust on the engine with the amber fan vibes all the way to idle. Immediately advance the throttle slowly back to its normal thrust setting. Make sure both throttles are matched and that thrust is now correctly set on both engines. In-flight demonstrations have shown that throttle manipulation is effective in reducing fan vibes back into the green range about 50% of the time. If fan vibes have recovered, make a note in the maintenance log that fan vibes had turned amber and continue the flight. If the LP vibe display returned to amber when thrust was restored, execute a descent per the guidelines on the next two slides. DFDR analysis has shown that if fan vibes turn amber above 30,000 feet, and the increased vibe level is not associated with possible ice buildup, an altitude reduction of 4,000 feet or more is effective in decreasing fan vibes below the amber level. For example, if you are climbing through or cruising at flight level 320 and the vibe gauge turns amber, ask ATC for an altitude change to flight level 280. The act of reducing cruise altitude involves throttle manipulations similar to that described on the previous slide. N1 speed will be moved away from the resonant frequency, causing the elevated vibe level. In-flight demonstrations have shown that reducing cruise altitude provides a much greater chance for success in recovering fan vibes than throttle manipulation alone. Attempting the throttle manipulation technique before executing a descent is still worthwhile because it does not involve ATC assistance. If fan vibes turn amber while operating below 30,000 feet, an altitude reduction of 2,000 feet or more will help decrease the vibe level. For example, if you are climbing through or cruising at flight level 280 and the LP vibe display turns amber, ask ATC for an altitude change to flight level 260. After the altitude reduction is complete, if fan vibes remain amber 10 seconds after the last throttle adjustment, accomplish the QRH procedure for engine abnormal vibration, which is found in Non-Enunciated Procedures 1-17. The 4,000 and 2,000 foot altitude recommendations are not absolute. There is no harm in descending lower than 4,000 or 2,000 feet. Post-flight analysis has validated that an altitude reduction is an effective technique in reducing fan vibration. Once the altitude change is complete, verify your fuel quantity to review fuel planning for the new lower cruise altitude. To be clear, the stated goal of this presentation is to dispel the misperception among flight crews that an amber vibe reading immediately equates to severe engine damage. We have established in the early part of this presentation that when no other engine problems are noted, there is minimal risk associated with a vibe reading that just turned amber. With that in mind, GE recommends completing a throttle adjustment followed by an altitude reduction before executing QRH procedures. If the throttle adjustment or altitude reduction brings fan vibes back into the green range, QRH procedures will no longer be necessary and the flight can be continued. If increased vibe levels can be attributed to ice buildup in flight due to operations in IMC, skip the throttle adjustment and altitude reduction and go directly to the QRH. Reference Engine Abnormal Vibration, Non-Enunciated Procedures 1-17. As a reminder, make an entry in the maintenance log anytime the fan vibe reading turns amber in flight. Do this whether or not you are successful in getting the vibe level back to green. Your logbook entry allows the maintenance team to schedule a retaining pin reloop at their earliest opportunity. The retaining pin that holds the fan blade to the fan disc needs lubrication to allow the fan blade to rotate into position. Lubrication deterioration allows the fan blades to bind and not find their natural spinning position determined by centrifugal force. As retaining pin lubrication continues to degrade, more fan blades tend to bind around the circumference of the engine. Pilots see this as an increase in fan vibes. Fan vibes operating anywhere between 0 to 3.9 units, which means the LP vibe digital reading in the cockpit remains green, is acceptable and will not harm the engine. There is no need for both engines to operate at the same N1 vibration level. Stuck fan blades are the most common cause of amber vibe readings in flight. This does not warrant immediately shutting down an engine. If fan vibes simply cannot be brought under control, yet all other engine parameters are operating normally, it is better to keep the engine running at idle. An engine at idle will keep your AC generator and hydraulic pump operating. If the engine has developed a problem that is not associated with bound fan blades, other engine parameters typically will operate outside their normal range. If your engine is operating normally in every respect, with the exception of the amber vibration display, the problem can be considered bound or stuck fan blades. Consider a throttle adjustment or altitude change before executing QRH procedures. An engine problem will be accompanied by more symptoms than just an amber vibe reading. Here is a partial list of what you can expect to see if an engine problem develops. High ITT or an ITT exceedance, engine stall, engine unable to make takeoff or climb thrust, fan or core vibes, high oil temperature, low oil pressure. Note that fan vibes can be part of the symptom list when an engine problem is encountered. If an engine problem does develop, execute QRH procedures according to the warning, caution, or advisory message displayed on the ICAS. When executing QRH procedures, if fan vibes cannot be controlled or reduced to within normal operating range, it is not recommended that an engine be shut down unless there is another indication of a severe engine abnormality, i.e. an ITT exceedance, low oil pressure, or abnormal HP vibration. If you would like to learn more on the subject or have questions about any of the material presented today, please feel free to contact me.